We're on module 10.09, which is free energy and equilibria. So we're going to go back to thermodynamics. Recall that the phrase thermodynamically favored means that products are favored and delta G is negative. In this module, we learned that a large value of K means product is favored, which means that we can put the ideas of K and delta G together. At equilibrium, there is no net change in the concentration of products and reactants. The relationship between Gibbs free energy and the position of equilibrium is related by the equation shown right here. Now, before we get into this, let's take a look at this graphic that I have up above. I've shown this before in the notes. We have this arrow with Kc over the top of it. At the blue end, the value for Kc is very small. The reaction proceeds hardly at all. At the red end, K is going to be very large. Remember that products are in the numerator, and the reaction proceeds nearly to completion. In the middle, we have appreciable concentrations of both reactants and products. There is a special point at Kc equals 1 or Kp equals 1, where delta G is exactly 0. Neither products nor reactants are favored. If, on the other hand, K is very small, then delta G is going to be very positive. If K is very large, delta G is going to be very negative. Now, if we are going to use this equation, delta G equals negative RT ln K, let's make sure that you use the correct form of R. So there are three different forms of R on the AP equation sheet. Your big clue here is that G, Gibbs free energy, refers to energy. And notice joules is part of the expression for R. So make sure you use the correct R. So special note here, use the correct R value. This is one of the most common errors I see students make anytime they're using R. Okay, so let's take a look at what we know. If delta G is negative, the reaction products are favored, thus K is greater than 1. Remember that we can think of K as being products over reactants and raised to their respective exponents matching the coefficients. So if we have a lot of products, we're going to have a high value of K and delta G is going to be negative. Likewise, if delta G is positive, the reaction products are disfavored and K is less than 1. Remember, K is never going to be negative. It's going to be a very small number, but K is never negative. So we're just going to run through these calculations. So make sure you've got a calculator. So let's look at this one first. A calculation using delta G reaction equals negative RT ln K. We are given this reaction right here, and we're given a value of Kp. So we just plug everything in. So we write delta G equals negative RT ln K. So delta G is equal to negative 8.314. Remember, this is joules, moles, and I'm just going to go ahead and write the whole expression in here. Moles negative 1, Kelvin's negative 1, because I want you to do is hone in on that joules. Times our temperature, 25 degrees is 298 Kelvin. And then we're going to take the natural log of 1.7 times 10 to the 12th. When we do that, our answer is going to be negative 69772 joules per mole. Notice our units are in joules. If we want to convert by kilojoules, you're just going to divide through by 1,000, so that would be negative 69.8 kilojoules per mole. So what I want you to pay attention to here is make sure that you keep track of the units on R. You can rather easily miss the point by not keeping track of the correct units. Now we're going to go the other way. Consider the reaction at 40 degrees C. And now we've got a slightly different reaction where delta H is negative 163 kilojoules and delta S is plus 148 joules Kelvin. And I should have had the moles in there, so let me just draw those in real quickly. What is the approximate value for Kp for this reaction? Well, remember delta G equals delta H minus T delta S, okay? So what we're going to do is plug the values in that they gave us for delta H and delta S. So that is going to be equal to negative 163 minus, and I've got 40 degrees Celsius, and 40 degrees Celsius is 313. So 313. And now I'm going to be multiplying it by delta S. And I have to remember to turn this into kilojoules. 0.148. I was trying to put too many zeros in there. Let's get rid of that. Wow, that didn't work. There we go. 148. All right. So what I did here was converted the value of delta S to kilojoules, because otherwise my units are not going to be consistent. So what I end up with is delta G is equal to negative 209.34 kilojoules per mole. Now I'm going to use that delta G is equal to negative RT ln K. Once again, I'm going to have to keep track of what's going on in the units, because delta G, I've just figured it out in kilojoules, but my R value is in units of joules. So I need to get everything into the same units. So I'm going to, and you can convert one or the other. So I'm going to choose to convert my value of R to a kilojoules value. So I'm going to stick with kilojoules. So I'm going to have negative 209.34 is equal to negative 0.008314. So I converted 8.314 joules to kilojoules. 313, there's my temperature, ln of K. When you do that, you have that 80.4 is equal to ln K. And remember what that means is we take E and we raise it to the 80.4 power. And when you do that, you get, I think when I just did this, I got 5 times 10 to the 34th. What I will tell you here is this value will also actually changes very rapidly based on what's going on. So if you round more or less, that value will change in a hurry. What the graders are going to be looking for is that exponent in the right ballpark? Since you're using it as an exponent, even a little shift in rounding will throw your answer off. It looks like a lot. So really what they're going to be looking at is that exponent. Okay, so I have one last problem here for you. And it's also kind of a review. It really is a review problem. So I'm going to pause and let you guys work through it. And then I'm going to go ahead and put up the answer for you. So let me go ahead and pause. Now, as we look at this table, there's a couple of things missing. We've got question marks under that delta H. And so remember, again, going way back, anytime we have a pure substance, the delta H of formation value is 0. So just in case you've forgotten that, I've put that in there for you. All right, let's take a look. This was a big long one and required you to put together some things from the past. So you had to figure out that delta H is negative 1652 kilojoules per mole. And then you had to figure out that delta S was negative 543 kilojoules per mole. Then you plugged into delta G equals delta H minus T delta S, remembering to convert your value for S to kilojoules. At that point, you were ready to, well, you figured out you had negative 1490 kilojoules per mole. Then you used delta G equals negative RT ln K, remembering that R, the units are in joules, so you need to convert it to kilojoules. So we plug that in. We have delta G equals negative 0.008314298 ln K is negative 1490. ln K is 601, and so you get a value of K e raised to the 601 power. Now, if you have a newer calculator, you will get a value. However, I have an old TI-84, and it gave me an error. Overflow, okay? If this happens to you, don't panic. You're on the test. You just write K equals e to the 601 and go ahead and make a little note, error overflow on calculator. They're going to accept this as an answer just fine. They realize some people have older calculators. Okay, we are done with delta G equals negative RT ln K.